Next speaker is Olaf Lechtenfeld from Leibniz Universität Hannover, and he's going to talk about stability of cosmic young fields. When we have 5 minutes left, I will let you know, Olaf. So please go ahead.
Okay, thank you. So yeah, thank you very much for having me and allowing me to this beautiful conference, even though I would rather like to be in person at the place. But it gives me the opportunity to speak about something that I've been doing with my 2 PhD students lately. And it's a piece of traditional mathematical physics, nothing to do with string theory, just standard model physics, essentially. And it explores the possibility of having explicit Yang-Mills-Higgs solutions, Einstein-Yang-Mills-Higgs solutions in the context of early cosmology, perhaps, and their stability. So well, first of all, let me excuse me for the writing. I'm exploring a new device, which is an e-book tablet, which allows for a very nice feeling of writing. And I thought I'd try this for this conference. It's much faster in preparing. Okay, anyway, I hope my handwriting is visible. So the whole thing starts with a tale of 3 anharmonic oscillators. Here is the Einstein-Yang-Mills-Higgs system. Here you have the Einstein gravity, here you have SU2 Yang-Mills, and a Higgs, the usual standard Higgs sector. And here you see an anharmonic that is well known. Okay. 2 more anharmonic oscillators will appear soon, because I now assume SO4 invariants and a spatially closed universe. So here is the Robertson-Walker metric with a cosmic scale factor in co-moving time. And I switch to conformal time, tau here. And you see, of course, because of the symmetry, the closed universe, there is an S3 spatial slice here. So that's the metric of the 3 sphere. The only SO4 invariant Higgs field is 0. So in this setting, we're sitting at the local maximum of the Higgs potential, which will then provide a cosmological constant. Finally, the Yang-Mills field, being SO4 invariant, must have the form written here. It is given in terms of 3 left invariant 1 forms on the 3 sphere, the 3 generators as of the SU2 gauge group. And there's only left a scalar function of the conformal time tau, which I parameterize in this way. So psi parameterizes my Yang-Mills field, A of tau parameterizes my metric. And one can get these objects by using the identification map and using the Maurer-Cartan form, expanding it into left invariant vector fields. You can read off the left invariant 1 forms. Now, I reduce the action now to this SO4 invariant sector, and then 2 more anharmonic oscillators appear. The group, the gravitational part that is in standard textbooks in this conformal time variable takes the form of an anharmonic oscillator, however, with a wrong sign kinetic term. That's, of course, gravity. But also the gauge field takes this form. This function psi is a mechanical problem with an anharmonic harmonic oscillator, but the gravitation part has it upside down. This was found in the 70s, essentially, by these people, but not much explored, it seems. T prime is the lifetime of the universe, so in the conformal time. Now, these 2 systems are almost decoupled. The only coupling is due to the Wheeler-DeWitt equation, which relates the energy, the gravitational energy here in this gravitational system, to the mechanical energy of the Yang-Mills system. These are conserved quantities. And this is because the Yang-Mills system in 4D is conformal invariant, so the equation of motion do not feel the scale factor. On the other hand, the Einstein equation sees the Yang-Mills field through the stress tensor, but the stress tensor only contains this conserved mechanical energy E here in it. And so it leads to a dependence of this gravitational energy E prime through the energy momentum tensor on the mechanical energy E. So this is exactly this relation. So there's just a one-way coupling, and it's easy to write down the classical solutions explicitly. I give it here for energies above the critical value here. So if the energy is well above here and well above the critical value here, then they're just given by standard Jacobi elliptic functions. And this parameter K, the modulus, is related to the energy. And this is the period. K is the complete elliptic integral of the first kind. And similarly for the gauge, for the scalar, for the scale factor. Now here's some plot of typical behavior of the function psi. It is periodic. And the scale factor, when I'm above this local maximum here, then I get a divergence at the finite lifetime. So at finite conformal time tau, the universe goes into a big rip. Now what I have been looking at is perturbation around these classical Yang-Mills solutions. So let's take the classical solution parameterized by the scalar function psi as a background and perturb it and linearize the full Yang-Mills equations. Okay, this linearization problem then is best expanded into the different modes. So this phi has several indices. I expand it here into the group generators, into the one forms or the tau, and into a full set of S3 harmonics. This is a spin, and these are two other quantum numbers, labeling these S3 harmonics. So the components of this perturbation are denoted by phi here, and they carry these various indices, and they're just function of the conformal time tau. On these indices act here the isospin T. The spin, so on this index A, 1, 2, 3, act the spin S, and on the M and N indices act the angular momentum, the orbital angular momentum of our SO4 symmetry. There's two copies of SU2, an SU2 left and an SU2 right acting on these indices. So here we have basically a group theoretical problem, various SU2 groups coupled, well, they enter in the system. So this is spin 1, L squared is equals R squared, this is a spin J, and these are the ranges. Well, we can introduce fully covariant derivatives and the Lorentz gauge, which then expanded in this notion looks like this. Here's the background dependence. And the linearized equations of motion look like so. Okay. And here, this problem was investigated by Hossotani in the mid-80s for the very simple, for the simplest mode, namely psi equals 0. If I go back for a second, if I can, psi equals 0. Well, where is it? Yeah, psi equals 0 is just the what is called the meron. It's 1/2 EATA is the solution, basically sitting locally unstable here on this local maximum, complete constant solution here. Okay, but we investigate this problem now in full. Here's the fluctuation problem. And the fluctuation matrix, which should be diagonalized, has two blocks. And they're coupled here by the derivative psi dot. So on the two blocks take this form. Here, for example, there's a linear combination of L squared, L plus T squared, L plus S squared, and L plus T plus S squared, and some constant. So you see here is a problem of coupling of three angular momenta. So we have L, T, L, and S coupled. And we cannot diagonalize all these combinations, but we can diagonalize, for example, L squared, L plus T squared, and L plus T plus S squared, so U and V. V is the sum of all angular momenta. And so I go to such a basis. And then since one can see that L squared commutes with the fluctuation matrix, we can decompose into different spins J. And the full angular momentum, full spin V, all components commute with omega squared. So we have a degeneracy in this quantum number V here. Okay, so what happens then for the summing of the angular momenta, we get irreducible representations of L plus T and L plus T plus S. We have to couple spin J with spin 1 and spin 1. and we get these different representations of SU2. When you couple J plus 1 times 1 times 1, you get this 5 different angular momenta values for V, for the V spin. And here for the U spin is in this block N bar, and the V spin is responsible in this block N. So ultimately, we have some degeneracy here, and these blocks will get coupled, first of all, through this term L plus S squared, and then ultimately with this block through the off-block diagonal piece here. Okay, so in the end, you can solve the problem.
5 minutes, Olaf.
5 minutes, okay, thanks. We must still impose the gauge condition. And it turns out that the eigenmodes are given, well, for the two extremal sectors here, J minus 1 and J plus 1, they don't mix. There's no degeneracy. They can be explicitly written down. You see that for the non-extremal sectors, we get a characteristic polynomial here of order 3 or of order 4 even, and we have to compute its roots to get the eigenvalues, the eigenmodes. Because of the gauge condition and the gauge freedom, two of the 3 roots here are not physical, and here 2 of the quartic of the 4 roots are not physical. So we end up with a number of physical fluctuation modes, omega labeled by J, V, and some degeneracy index, and they're still functions of tau because they depend on the background function psi, which labels the fluctuations, labels the time-dependent background solution. So we have to solve Hill's equation, and Hill's equation has a 2-dimensional solution space, but it's very difficult for an arbitrary time-dependent function. However, for the simplest case, an SO4 singlet mode, we can actually solve, because then one solution is just the derivative of psi, and the other solution can be then, of course, obtained explicitly. And if you look at this function psi, it is omega squared, the frequency. It has this periodic behavior, but it becomes negative at some points. So signaling instability, which happens when the particle in our double weld potential hovers near the local maximum. Then the second derivative of the potential is negative there. So we see an instability. In fact, we can plot all the modes. Here's some plots for the J equals 0 sector. There are 4 different modes. The behavior at a very high energy just above the critical point, just below the critical point, and very near the true vacuum. And for J equal 2, coupling spin 2, you get more complicated pictures. But we have all the explicit behavior of these functions over time. Now, to get better control, we can look at the stroboscopic map, which is convert the second order fluctuation equation in a linear equation. The system of linear equations, solution is given by the time-ordered exponential, which is not periodic, but it is periodic when you go over one period. When you map over one period, the so-called stroboscopic map provides this kind of time translation in integer multiples of the period, and you can try to calculate this exponential, but it's not trivial because there are some non-trivial integrals which in general cannot be done. However, Floquet theory comes to our rescue in a sense, because we know that the fundamental principal solution of the system is given by a periodic matrix times some exponential, which shows you a growth, a possible growth. It's related to the Lyapunov exponents of the system. So the eigenvalues of this matrix R, or this matrix M, will tell you about stability. So if the trace of this matrix is bigger than 2, then you have an unstable situations like a boost, a cosh. You get a linear, marginal system when it's exactly 2, and for less than 2, you have a cosine, then it's rotation, and it's stable. In the simplest case, in fact, we can calculate it. So the solution of the fluctuation mode is like that. The second fluctuation mode is like that. And here you see not only a periodic part, you see a linear growth piece. So here is linear in the time. And therefore, when you evaluate the monotony matrix, you get a Jordan matrix form. This means that we are in the marginally stable situation. And there is a linear growth rate of the system, explicitly given in terms of elliptic integrals. And you can study it numerically. So in this case, however, we can do better because for the SO2 singlet case, we know the 2-parameter family of solutions. They're given by our functions psi, labeled by the energy parameter and the shift in t. And we can exactly solve for the perturbation eta, which satisfies a nonlinear equation. So that's the full equation for the perturbation beyond the linear regime. And if you look at that, you see that when you do not change the energy in your perturbation, you still remain periodic. But when you change the energy, you get this linear onset of linear growth, but eventually it comes back and you get the beating behavior, which is what you expect when you take a difference of two periodic functions whose periods is slightly not equal. Okay, so of course, because we have a bounded system, all the perturbations eventually have to come back. So here's a plot of the periodic solution. Here's a plot of the exact linear approximation, but it is only the first part. It will come back. So finally, in the last maybe minute or two, let me just propose some application to cosmology of all this, because what happens with the Higgs sector? The Higgs sector was unstable. Phi equals 0 is the local maximum. Now the Higgs sector couples to the gauge field here, and it couples to the cosmic scale factor. So you see, when you write it, there is again a mechanical problem for the fluctuations in the Higgs sector, and the potential U has a negative part. So when the cosmic scale grows big enough, it will overcome this piece. So in some sense, what happens here is we have a negative, an inverted harmonic potential, but nevertheless, it can be stabilized by a gauge field in here, which is wildly fluctuating. As you saw in our solutions, the gauge field fluctuates. So it is a parametric resonance problem, like the inverted pendulum, that you can stabilize by moving the pivot up and down. And you can calculate the conditions which guarantee stability. And it turns out, though this was done by Friedan in a nice paper last year, and he found out that when you define the onset of the electroweak phase transition exactly at the scale factor where this stability is violated, then you can relate it to the energy of your mechanical system, E. And it turns out the energy in natural units, this is a dimensionless number, is huge. So you have actually a large number of oscillations. And when you put in the scale, the gravitational scale in the weak scale, you get that the scale, the gauge field will oscillate about 10 to the 17 times in the lifetime T prime of the universe. So the scenario is like in a very early universe, you could have such cosmic gauge fields. They are wildly oscillating and they stabilize the Higgs potential. And eventually, when the scale factor gets big enough, it becomes destabilized, the electroweak phase transition sets in, and we go out of the SO4 symmetric sector. So the obvious questions, is that stable against thermal fluctuations? What happens to the higher modes? Why should we have SO4 symmetry? And what happens at the transition? How much expansion do we get? How much CP violation, for example, because our solution, our gauge field is CP odd. And if we get enough details to this scenario to make it a testable thing. Thank you very much. And Happy New Year.
Thank you very much, Olaf. Thanks a lot. There are any questions? I can see any. From Mikhail. Mikhail, please go ahead.
Thank you all for your interesting talk.
You are mute, Mikhail? Okay.
I hear him.
My question is, in your analysis, there appeared the system of coupled oscillators with time-dependent frequencies. So
Yes.
my question is, it is known that with such a system, it is one can be related Yermakov-Lewis invariant with oscillator with time-dependent frequencies. So my question is, those Yermakov-Lewis invariants, do they play some hidden role in your system?
Okay, I don't know about these invariants, to be honest. Maybe you can point me to a reference, but I studied Hill's equation a bit, because this is a prototypical case of Hill's equation, and there are, of course, some special cases where one can do better. But I haven't found any reference to this invariant, I must say. So are you sure that it's true in any kind, for any kind of periodic behavior here? Such invariant exists?
But in your conformal factor, there appeared some periodic conoidal type periodicity.
But the conformal fact in the cosmic solution, yeah. But here we have only one period until the universe ends its lifetime. So for when we are below the critical point, oscillating around here, we just look at a solution just grows and then comes back to zero. That's just one where a big crunch appears. That's just 1/2 period. Or when we are above, then the universe, just the scale factor goes to infinity. That's what happens here. So of course it can be periodically continued, like the cotangent function or the tangent function can be continued, but the lifetime of the universe ends at this point, right?
Okay, but I don't know, you can try to make some analytical continuations. It is, you in principle,
Sure,
you could, and then this will not, in such a way, the periodicity will not enter into the game.
No, you see, but these functions psi here, this function psi will enter into the frequency. So my frequency of my fluctuation problem is a function of this Jacobi elliptic function psi. Yeah. So the periodic, I know exactly the function omega squared of time, and it is some polynomial essentially of this psi. For this kind of periodic behavior, I want to solve the fluctuation problem, and I have in some cases.
Okay, thank you.
Mauro, maybe a quick one. We're almost on time.
Okay, so it's a bit speculative, so I can just pose it and maybe comment. You can comment afterwards. So as far as I understand, Fouquet theory is like the time analog of block theory in condensed matter or crystalline structures. So
Exactly, yeah.
if you imagined a QFT with 2 times, like Itzhak-Barr's theories or so, could it be meaningful to think about the topology in that time, 2 times dimension, and do some kind of analysis as the one you do here?
Oh, I don't know how to do this with 2 time variables, but okay, that would require an extension, right, of Fouquet theory to a partial differential equation, I guess, with more than 1 time variable. I'm not aware of that.
No? Okay, too speculative.
I've not seen in the literature such an extension. Perhaps it exists, yeah.
Okay, thank you very much.